So, hello everyone, I'm Sachin, and we will proceed with our third and hopefully final lecture on nonlinear response theory. Uh, Along with this lecture series, this three lecture series, we've had a lecture on linear response theory and a couple of videos on density operators, I suppose. So, hopefully, this will be our final lecture in deriving the analytical expressions for our third order nonlinear optical response functions under the second cumulant approximation. So as of now, we have derived R1 through R4, where R1, uh, T1, T2, T3, I will mention this once, is equal to mu Eg to the power 4. Again, we are considering a simple two-level system. And then you have your coherence minus I omega Eg T1 plus T3, as this is a non-rephasing process, and this is your for your two-level system corresponds to your non-rephasing stimulated emission process. And you have your dephasing function f1, which is a function of T1, T2, and T3. Likewise, you have R2, R3, and R4. To save some time and space, I will write this as R1 slash R4. And here I can put in an F1 slash F4. So these are your non-rephasing processes, and you have two dephasing functions F1 and F4 to define the two non-rephasing processes. And then for your rephasing processes, which are your rephasing stimulated emission and bleach, we can write a general expression as follows, where you have your oscillator strength, and then here you have a minus I omega Eg, T3 minus T1, and you have the corresponding dephasing functions for these two processes. So, just as a reminder, I think I will write down F1 through F4, and then we will begin our evaluation of F1 through F4. So, F1 looks like this. You have a negative time ordered exponential from T1 to T1 plus T2 of the energy gap operator encoding the fluctuation in transition energy of the particular two-level system. And then you have a positive time-ordered exponential from 0 to T1 plus T2 plus T3 of the same energy gap operator. So this is an equilibrium bath ensemble average, and then likewise you have a negative time ordered exponential and a positive time ordered exponential. For F2, the negative time ordered exponential runs from 0 to T1 plus T2, and dot dot dot, and then the positive time ordered exponential runs from T1 to T1 plus T2 plus T3, U E G tau D tau. Now, likewise, we have F3, which is your dephasing function corresponding to your rephasing ground state bleach process. And again, we have a negative time ordered exponential and a positive time ordered exponential. This runs from T1 plus T2 to T1 plus T2 plus T3, UEG tau, T tau, then bath ensemble average. And F4 is a bit unique in the sense that it corresponds to the non-rephasing bleach process. So all the interactions of the light field are with the get side of the density operator, and hence you just have two positive time ordered exponentials, one running from t1 plus t2 to t1 plus t2 plus t3 of the energy gap operator, and the other one running from 0 to t1, so 0 to t1 of u e g tau d tau, then uh, again a Bath ensemble average. So these are your F1 to F4 expressions which we came at in the last class. So in the lecture where we derived the the line shape for a linear response experiment. So, from linear response theory, uh, we evaluated a simple dephasing function in that case, which was, uh, I would urge you to go and revise or relook that lecture. But in that case, we had a dephasing function which only contained one positive time ordered exponential which went from 0 to t1 in that case, because in a linear response experiment, you have an incident light field, and then you measure the response of your system as a function of t1. So you can construct a simple Feynman diagram to visualize this. You are in the ground state. You have a light field which interacts with the ground state, pushes you to a coherent state, and then you have the emission of a signal field, and this is time t1. So essentially this t1 is the time after which your light field is incident on the sample, and then this t1 can be scanned. So to calculate the signal emitted from the sample at various t1, and then this is what your dephasing function is. For notation, I will call it ft1, and this contains information on your spectral line shape in your linear absorption spectroscopy experiment. So what we did here was we expanded this out. So if you expand this out, since it's an expectation of a positive time ordered exponential, when I expand the positive time ordered exponential and take its expectation, I'm just getting various moments of the distribution. So what do I mean by that? Let me just take an let me just expand the positive time ordered exponential. So I get 1 or identity minus I upon h bar from 0 to t1. You had e.g. tau d tau plus minus I upon h bar square, the integral from 0 to t1 d tau 0 to tau d tau prime, and then you had eg tau, you had eg tau prime, and so on and so forth, right? And sorry, and then you take a Bath ensemble average. So when you consider this Bath ensemble average on each and every term, you just get identity or 1 minus I upon h bar 0 to t1, the Bath ensemble average of the linear term plus minus I upon h bar 0 to t1 d tau 0 to tau d tau prime, and you had eg tau, you had eg tau prime, the Bath ensemble average, and you have subsequent third order, fourth order, higher order terms. So in general, if you have some observable, let's just call it a, or you just have some variable a, but here since we're doing quantum mechanics, let's just stick to an observable a, and you want to write its moments down. Its first moment is given this way. The second moment is given this way. Its third moment is given this way, and so on and so forth. So these are its moments, right? So intrinsically, by this positive time ordered exponential, the expectation of it is in a sense giving the moments of the energy gap operator. Of course, you have to be careful here because it's a time ordered exponential, and yeah, it's not as simple as a simple distribution of some random variable, right? So it's not like you have some operator a and then its moments are a square, a cube, the expectation values of those, right? So it's not that simple. And likewise, you can define something which are known as cumulants. So the cumulants of a particular observable, let's just say a, denoted by a hat c for the lack of a better notation, a square c, and then a cube c. So these are known as your cumulants, and the cumulants are just an alternative representation to moments. This is just a short digression into statistics so that it helps with the understanding. So it's an alternate representation to your moments, and any cumulant can be written as a linear combination of moments. So let me note that down. Any cumulant can be written as a linear combination of moments. So essentially, it's just an alternative representation. For your information, the first cumulant, which is a hat, c, is also equivalent to your first moment. So let me just write that down here. So a hat c, your first cumulant, is equivalent to your first moment and is your mean of your distribution. Of course, the expectation of the observable will be your mean, right? And then you have your second moment, which is your variance. And your variance can simply be written as your second moment minus your first moment, your mean squared. Right. So this is the basic definition of variance. So likewise, and uh, so on and so forth. Your third moment, your third cumulant, I'm not going to write it down, but is known as your skewness. And your fourth cumulant, I apologize if I said moment. I meant the third cumulant is skewness. The fourth cumulant is known as kurtosis. But we won't digress into these, and we won't even need these for what we're doing right now because we're going to restrict ourselves to our second cumulant. So it's just an alternative representation. And sometimes what this is known as is a moment generating function, also known as MGF. So, what is a moment generating function? So, if you take the exponential of some operator A and calculate its expectation, this is known as your moment generating function or MGF. Very simple to understand that I expand this exponential A, I get one identity plus A hat plus A hat square upon 2 factorial, and then I take an expectation of this. So I get identity plus the expectation of A hat plus the expectation of A hat square over 2 factorial and so on and so forth, right? This is not the very rigorous definition of a moment generating function because for a moment generating function, what people will do is introduce some dummy variable into it too. So something like a t or an x. And then what they would do is, let's say you introduce something like exponential a hat x. So what they would do is they would get identity plus a hat x plus a hat square x square upon 2 factorial, blah, 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 blah. You take an expectation. So this expectation will only act on a hat. So you get identity. Let me not put the hat because I haven't been putting it at other places. So expectation of a hat x plus expectation of a hat square upon 2 factorial x square, blah, blah, blah. And what they will do is they will take this moment generating function, call it m as a function of x for this random observable a hat. So I'm calling it this. So you can call it m a x. And what they will do is differentiate it. So if you differentiate this once, you get your first moment. And then you differentiate this twice, and then you get your second moment, and so on and so forth. So that's why this is known as a moment generating function. And the moment generating function is defined more rigorously with some random dummy variable x or t or whatever introduced to it, and then they take derivatives. But a loose definition would just simply be this one, where, sorry, okay. Loose definition would just definitely just be this one, where you're essentially just generating your moments of all your moments of a particular operator or observable. So in this case too, here you're just this sort of function is just generating your moments of your energy gap operator. Of course, it's a bit more complicated because you have your time ordered exponentials and whatnot, right? So let's not worry too much about this. Now, as I just mentioned, that the cumulants are just linear combinations of your moments. So that's why when you take your moment generating function, or the function which is the expectation of the positive time ordered exponential from 0 to t1 of u e.g. tau d tau. And as I just discussed, that the cumulants are just linear combinations of the moments. So this is generating my moments. So I just want it to be a linear combination of those. So what I can do is write it as an exponential of sum over n, let's just say from 1 to infinity of 1 upon n factorial kn, where kn is the nth cumulant of this time ordered exponential, or this energy gap operator, right? So this distribution, right? This positive time ordered exponential and then the energy gap operator within it. Right. So what you could do after this is to take a ln of the expression on both sides. So as I previously discussed, so you take ln of this expectation of this positive time ordered exponential from 0 to t1 u e g tau d tau, right? And then you have from n equal to 1 to infinity 1 upon n factorial kn, where kn is the nth cumulant, right? So it's quite obvious to see that since this function, now the ln of the moment generating function is generating a linear combination of cumulants, as you can see on the right hand side. This in statistics is known as your cumulant generating function. Of course, people define it more rigorously in statistics, but for our understanding, this is good enough. So this is like a cumulant generating function, and you can generate your cumulants for this positive time ordered exponential of your energy gap operator. So as we did in the previous class, you get 1 plus something, which is your, so which you get by expanding your positive time ordered exponential. And then ln 1 plus x is approximated as x minus x squared by 2, and so on and so forth. And then you generate your cumulants, which we recall. And what ends up happening after doing this procedure, where we only consider cumulants till second order, uh, we do not consider cumulants higher than second order because of the central limit theorem, which allows us to assume that these fluctuations follow Gaussian distribution. Right. So what you end up getting is, for your dephasing function, which encodes your spectral line shape, you get u e.g. tau d tau, and under the second cumulant approximation, it is approximated as e raised to the power minus g e e t1, right? And this is just your dephasing function under the second cumulant approximation, and then this function GEET is known as your line shape function. And then your line shape function, as we previously described, is the double integral of your FFCF, your frequency fluctuation correlation function, which we denote by CEE tau prime here. And then this CEE tau prime is just 1 upon h bar square u e g tau prime u e g 0 uh, path ensemble average, or the other way of writing it would be 1 upon h bar square, and you can write it as CEE as a function of tau prime, or you can write it as CEE as a function of tau tau prime, which means that you can write it as UEG tau UEG tau prime traced over, the Bath ensemble average. I will prove the equivalence of these two integrals in a little while. I suppose I haven't done that previously. What I mean to say is the integral from 0 to t d tau, 0 to tau d tau prime of this 1 upon h bar square. Forget about that, but this one, u e g tau prime UEG 0, and this one, the 1 upon h bar square, 0 to t d tau, 0 to tau d tau prime of UEG tau, UEG tau prime traced over, the path ensemble average, right? So I'll prove the equivalence of this very soon. Just a word of caution, I'm not trying to say that these two are equivalent. I'm trying to say that the integrals are, I should not use this, the integrals are equivalent to each other, and we will prove that soon. So this is what we derived in the previous class, where your GEET correlates your fluctuation in transition energies or frequencies of the two level system at an interval or a duration of time t. So it could be time 0 and time t. So let's say you generate your coherent state after the first light field is incident on the sample, and then you measure your fluctuation in transition energy at some arbitrary T1, right, in the actual expression, at some arbitrary T1 after you generate the coherence. So you're measuring these fluctuation in transition energies over that time, and that governs your spectral line shape. So we will prove this equivalence soon. And we had written this a little bit more generally, so let's go back to that general notation. Because GEE is very specific, we wrote it as G alpha alpha T. And then this G alpha alpha T again was 1 upon h bar square, 0 to t, t tau, 0 to tau, d tau prime of the 2-point energy gap correlation function, UEG tau, UEG tau prime, and this is a Bath ensemble average. And so, sorry, not EG here. This would be alpha G, U alpha G, U alpha G tau prime. And then this notation, which we had written out very clearly in that lecture, is just equivalent to this for the EG case, right? And then I will prove that you can write it like this too, which comes from here, right? And I will prove that in a little while. So now instead of writing it as alpha alpha, what I would like to do is write it as G beta alpha to be a little bit more generic, and to also introduce the fact that you can measure correlations between different transitions in spectroscopy. You don't need to measure the correlation of one transition with itself. I totally understand that for the case of our two-level system, right? We are confined to this situation where you're tracking one transition only. That's why both indices are always the same. So it will always be GEET, right? But it can also be beta alpha where beta is not equal to alpha. So it could be GIJT, GJIT, where I and J are two specific states your of a particular system, three-level system, four-level system, so on and so forth, right? So I would like to introduce this fact that this beta alpha might not need not be identical. So I will write it this way: 0 to t, t tau, 0 to tau, t tau prime, u hat, beta g tau, u hat, alpha g tau prime, but ensemble average. So what this essentially means is if I excite state alpha and probe state beta, what are this is not necessarily, but it's easier to understand this way that you're measuring the fluctuation. Okay, let me mention it in a better way. You're measuring how correlated the fluctuations in the alpha transition are to the fluctuations in the beta transition. So let's just say you have some common ground state for the sake of an example, and then you have the state alpha, and then you have the state beta, and then you have this common ground state. So you're measuring the correlation in these two transitions. That's what this uh, cross correlation sort of uh, energy gap correlation function does, right? So this is known as your cross correlation line shape function, and I hope that it's understood why it's the cross correlation line shape function when alpha is not equal to beta, of course. And then this 1 upon h bar square, you had beta g tau, you had alpha g tau prime is known as your it's known as your energy gap cross correlation function. But when alpha is not equal to beta, we call it the FXCF, or the energy gap cross correlation function. But let's not worry about that. Let's focus on the terminologies. So FXCF means your frequency fluctuation cross correlation function. I previously introduced you guys to your autocorrelation. When alpha is equal to beta, this G beta alpha corresponds to something like your GEET for your two-level system, right? So in that case, this G beta alpha is your autocorrelation, which I should call AC, line shape function, or simply a line shape function, like how I introduced above. I just called it the line shape function, right? So people call it the autocorrelation line shape function, or simply the line shape function. And when alpha is equal to beta, this C beta alpha, which we introduced above, uh, this sort of thing, which is just 1 upon h bar square, as I've written above. You had b g tau, you had alpha g tau prime. The C beta alpha is known as your FFCF, frequency fluctuation correlation function. And I have introduced this in the previous lecture, in that lecture where we calculated the linear spectral line shapes. It's known as the FFCF, a frequency fluctuation correlation function, where you track the correlations in the frequency fluctuations of one transition In the FXCF, you're tracking the fluctuation in transition frequencies of two distinct or separate transitions. So that's important, and I wanted to introduce this notation to you guys. Right. So let's continue with two properties or proofs of your correlation function and line shape function. So I wanted to introduce these proofs. I suppose there's uh, three proofs slash properties of C beta alpha and G beta alpha, right? So the number one would be you have C beta alpha as a function of let's say two coordinate time coordinates t1 and t2, which is as I previously described 1 upon h bar square u, let's say beta g t1 u alpha g t2, right? And I'm going to prove to you that this is equal to C beta alpha T1 minus T2, or the duration of time T1 minus T2. Right, this is quite easy to prove. You can just write this as 1 upon h bar square, and you have this energy gap operator, which is traversed in time t1 by means of your path Hamiltonian, as we have previously discussed. So you can just write this as e raised to the power I h b t1 upon h bar, your energy gap operator itself, and e raised power minus I h b t1 upon h bar. And I would do the same for the second case, where I have e raised to the power I hb t2 upon h bar u alpha g e raised power minus I hb t2 upon h bar. Sorry, I would also like to go back to the trace notation, 1 upon h bar square, then the trace over your path states with your path equilibrium density operator. And your path equilibrium density operator, as I previously mentioned, is a function of your path Hamiltonian for your canonical ensemble, which is just e raised to the power minus beta hp upon trace e raised to the power minus beta h B. So this is the form of your bath density operator as I previously described. So it is just uh, so it's just a function of the bath Hamiltonian. So the long story short for introducing this is that you can essentially move this around to the other side. So this e raised power minus I hbt2 upon h bar commutes with rho b. So we swap this order, we move this ahead, and then because of the invariance of the trace to cyclic permutations, we introduce it over here. So that's what I'm going to do. So you get 1 upon h bar square, trace over bath, and then you have e raised to the power I hb T1 minus T2 upon h bar. You had beta g, and then you have e raised to the power minus ihb T1 minus T2 upon h bar. You had alpha g rho b. So this is what you get. And it's quite obvious to see that this first term will just give you had beta g t1 minus t2. So it's equal to 1 upon h bar square, trace over path. Okay, we can go back to the old notation of the equilibrium ensemble, bath ensemble average, where you get u hat beta g t1 minus t2, u hat alpha g0, Bath equilibrium ensemble average. So this is equivalent to C beta alpha T1 minus T2. So you just, the people don't write this, so you can just write it as T1 minus T2. So it is merely a function of the difference in time T1 minus T2. And that's quite obvious from here that it only depends on the time difference between uh, uh, essentially T1 and T2. So that's the proof. So the proof is C beta alpha or your energy gap correlation function. Actually, this holds for good for any 2-point equilibrium correlation functions, but in our case, it's the energy gap correlation function is equal to C beta alpha T1 minus T2. So this is our proof number one, and it's quite important. So proof number two is um, the proof is you have C beta alpha again, and you need to prove that C beta alpha minus T is equal to C alpha beta T star. This is just your complex conjugate, right? So you got to prove this. So for your C beta alpha minus T, using our definition of our energy gap correlation function, you had beta G minus T here. You had alpha G0. I hope this is very clear that when I write C beta alpha minus T, this argument only pertains to this one here. As I've just proven about that if you write C beta alpha T1 minus T2 or any argument, just if you write a single argument C beta alpha T, it corresponds to the first argument here. And then because the entire idea is that it only depends on the time over which you measure the correlation of your two observables. So here the time over which we measure the correlation of the two observables turns out to be minus t. And then you just have to prove that it is equal to the correlation function over time t complex conjugated. So that's what we're trying to do here. And here you can write this out as e raised to the power minus I hb t upon h bar. Okay, to be more clear, I write it as I hb minus t upon h bar u beta g e raised to the power minus I hb minus t upon h bar. Right, so that's quite obvious. And we can go back to our trace notation if we wish. So it becomes 1 upon, sorry, there's an h bar square here. And then you have a trace over your bath states of e raised power minus I h b t upon h bar u beta g e raised to power I h b t upon h bar u alpha g, and then you have your bath equilibrium density operator. So now what you need to prove is that it is equal to C alpha beta T. So the number one thing which we have to do here is that uh, you need to bring alpha to the front of your correlation function. So you have C beta alpha minus T. So what we need to prove is that it is equal to you had alpha g t, you had beta g0. That's what you have to do, right? So it's quite simple to do this. The first thing I would do, which is quite obvious, is take this and move it here. And then it's quite obvious to see that e raised power I hbt upon h bar u alpha g e raised power minus I hbt upon h bar will just give me u alpha g at time t. So you get 1 upon h bar square, trace over path, and then you move it across. You get u beta g times u alpha g time t. So you should write u beta g 0, u alpha g at time t, and you have the Bath equilibrium density operator. Okay, so what you need to do now here is that you need to take the complex conjugate, right? So let's just say that you take the complex conjugate of this trace, right? So after this, what I will do is take two complex conjugates, because let's just say you have A complex conjugate, that just gives you A, right? So you can take two complex conjugates, you have 1 upon h bar square, and then you have one complex conjugate inside. So you take the complex conjugate inside the trace. So you take a trace of the Bath states, and then you're taking what I'm essentially doing here is complex conjugate, then another complex conjugate. So I take this complex conjugate inside the trace, and these since these are operators, and I'm taking the complex conjugate of the trace. So if I have like A, B, C, and then you're taking a trace of A, B, C, and then the complex conjugate of this, as I had previously mentioned, would just be the trace of C dagger, B dagger, A dagger, and then that should be equal to the complex conjugate of the trace. So it's a mathematical property. I hope that's, oh no, yeah. I need to erase all of this. One moment, please. Yep, so I can go inside, and then the Bath density operator is already Hermitian, so I write it as rho B. And after that, you have u hat alpha gt dagger, which is just equal to u hat alpha g t, and u hat beta g dagger, which is equal to u hat beta g, because these are all Hermitian observables. And of course, you can move rho p over here, which is equal to 1 upon h bar square, the trace over all your Bath states of u hat alpha gt, u hat beta g0, complex conjugate, which is just equal to c alpha beta t complex conjugate. So this concludes proof number 2. Right, so which means that c beta alpha minus t is equal to c alpha beta t star. So now let's come to proof number 3, which is the proof which we wanted to do early on, which is this. So we will work on this proof now, which is to prove that your g beta alpha t, which is 0 to t, d tau, 0 to tau, d tau prime, 1 upon h bar square, u hat beta g tau, u hat alpha g tau prime, Bath ensemble average, right? You have this, and you need to prove TP to prove, and it is equivalent to 1 upon h bar square, 0 to t, t tau, 0 to tau, t tau prime, u hat beta g tau prime, u hat alpha g 0. So this is something which I introduced early on. So I would like to prove this too. So now the easy and the first step to go about this is to just write this as u hat beta g tau minus tau prime u hat alpha g 0. I mean, this was just proved in our number 1 case. So you just have to introduce these time evolution operators and these time reversal operators, and then this result is very straightforward to prove. Then from here, where we have 1 upon h bar square, 0 to t, d tau, 0 to tau, t tau prime of u hat beta g tau minus tau prime u hat alpha g 0 trace for the path. What you can do is so just to realize that tau prime lies between 0 and tau. So it's just an integration variable which lies in this bound. So what I can do is just introduce a new variable, call it tau double prime, right? And make it equal to tau minus tau prime. So what that means is that tau prime is equal to tau minus tau double prime. This might be a little bit confusing, but what I'm going to assume here is that for the inner integral, please pay very close attention here. For the inner integral, tau will be a constant. For the inner integral, I repeat again, tau will be a constant and tau prime is the variable of integration. I'm just substituting this tau double prime as tau minus tau prime by looking at this, right? So this is a constant for the inner integral. Just wanted to repeat that one more time. So d tau prime is equal to minus d tau double prime. So what you get is 1 upon h bar square, 0 to tau, 0 to t, t tau, 0 to tau, which is again, in this case, your tau will be constant. And then you have d tau prime. Oh, sorry, I have to change the limits of the integral. So when tau prime is 0, tau double prime is tau from here. And when tau prime is tau, then tau double prime is 0. And from the d tau prime is equal to minus d tau double prime, which is there here. And then you have u hat beta g uh, tau double prime. You have u hat alpha g 0 bath expectation, right? And then you can get rid of this minus sign and change the limits of your integral back from 0 to tau. And what I could also do is revert back to my old notation from tau double prime to tau prime, because it's just a variable of integration at the end of the day. So I can go back to this. So 0 to t tau, 0 to tau, tau prime, d tau prime, u hat beta g tau prime, u hat alpha g 0. So yeah, so we just proved that these two cases are equivalent in deriving your line shape function g beta alpha t. Yeah, so that I hope that proves that, and that suffices. So these three proofs are extremely important. Now, before we go on to evaluate your cumulants, which I understand by now is getting really frustrating, we have some more properties on the integrals which we need to be careful of. Because we will, when we start evaluating the cumulants for this, for the third order nonlinear response functions, the dephasing functions, you'll realize that there's certain properties of integrals which are to be known, which are not that simple, so I will introduce them now. Um, Quite easy to observe that when we consider your line shape function, you have this sort of mathematical structure. You had beta g tau. I apologize if I missed the 1 upon h bar square somewhere because it's just a constant, so I keep on forgetting it from time to time. So you need to observe the structure. So this lower bound of firstly the inner integral, this goes from 0 to tau, and the outer integral goes from 0 to t. So this tau prime can lie anywhere from 0 to tau and is an integration variable, and tau can lie anywhere from 0 to t. So this sort of structure is needed for all my line shape functions when I do my cumulant expansion technique. So there's some properties which I would want to introduce right now. I think there's three properties of integrals, right? So the first property would be the integral from, let's say, 2 times t1 to t2. And this is very simple. It's like high school, uh, secondary school sort of stuff. It's just u hat alpha g, some arbitrary function, f of tau, d tau, integrated from t1 to t2 would just be 0 to t2. U hat alpha g tau d tau minus 0 to t1 u hat alpha g tau d tau. So if you assume some arbitrary function, which is like f of tau, as a function of tau from t1 to t2, and assume that it's continuous over this bound, then what you could do is integrate this function from, let's say, assume that it's continuous from 0 to t2. So that's as an assumption that it's continuous in this range 2, right? It's as you just assume that this f of tau exists in this range and has some arbitrary form. So what you can do is integrate this function from 0 to t2, which is this, and subsequently subtract this off. So what you end up getting is the integration region which you require. So that's property number one, and it is very, 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 very simple, right? So now let's go to property number two, which is this sort of double integral where let's say you have some time again t1 and t1 plus t2 t tau 0, oh no, sorry, not 0, t1 2 tau d tau prime of u hat beta g tau u hat alpha g tau prime. Just not going to write the h bar square right now. That's 1 upon h bar square. That's not relevant to the property. So let's not worry too much about that. So in this case, your both the lower bounds of your integrals are from t1, and this goes to tau, which is good, and then this goes to t1 plus t2. So this is kind of worrisome for one specific reason only, that if you look at your g functions here, your lower bounds start from 0. So I want to, like, like massage this equation of this form, which we will see while doing the cumulant approximation, to something which integrates from 0 to something. So this is worrisome when we do your cumulant approximation. So this worries us. So what we would want to do is we want to write it as some form which goes from 0 to something d tau, and then 0 to tau d tau prime, and then that would just solve all your problems there at that point. So that would be good. So how would we do that? We can prove it that this is equal to 0 to t2 d tau 0 to tau d tau prime u hat beta g tau u hat alpha g tau prime. And then this would look something like your line shape function. Of course, you have the 1 upon h bar square there. And how do we prove this? So step one, which is to worry about the outer integral in this case. And then step two would be to cater to your inner integral. The reason why I want to cater to my outer integral in this case is that once I worry about my outer integral, I'll have to change this bound too, because one of the bounds in my integral depends on the outer bound. So I'll have to change both the bounds systematically in this case. Of course, that is the case in our previous proof too, but in that case, it was just much simpler to deal with the inner integral itself and treat that uh, tau to be constant. So yeah. So in step one, this is just a lot of tau double primes and tau triple primes. So please bear with me. I will set tau prime as tau minus t1, and that the reason behind doing this is to quench this lower limit. So that can be satisfied very easily in this case, because when tau is t1, tau double prime will be 0. And when tau is t1 plus t2, tau double prime would just be t2. And then d tau double prime is just d tau. So you can write it as d tau double prime. And then your second integral runs from t1 to tau. So tau in this case would be tau double prime plus t1 d tau prime, and then you have your u hat beta g tau. Okay, we are going to write it this way, but you can also write it as u hat beta g tau prime, like how I previously told you guys. U hat alpha g 0. I think this will be easier to do the proof with, but I'm just going to stick with this for now. So you have u hat beta g tau, which is tau double prime plus t1, and then you have u hat alpha g tau prime. Now you do the same thing. Step 2 is you want to quench this lower limit. So to quench this lower limit, let me introduce something like tau triple prime, and that would be tau prime minus t1, because when tau prime is t1, tau triple prime would be 0. Let me write that down. And then when tau prime is tau double prime plus t1, tau triple prime would just be tau double prime. So this, right? You have d tau prime, in this case, d tau triple prime, and d tau triple prime is just equal to d tau prime. So that's why you can do that. And then you just have u hat beta g tau double prime plus t1, and then you have u hat alpha g tau triple prime plus t1. Right, and using the property which I just described, where essentially it only depends on the duration over which you traverse, but it's quite easy to see too that if I introduce my IHBT over H bar everywhere and work the math out, this will be equivalent to U hat beta G tau prime, tau double prime, U hat alpha G tau triple prime. I urge you guys to prove this if it is not clear already. And then I don't like these double prime, triple prime, blah, blah, blah. I'll just go back to my old notation of tau and tau prime. So you get 0 to t2, t tau, 0 to tau, d tau prime. You have u hat beta g tau, u hat alpha g tau prime. Right. So in turn, what you have done is it's proved. So you can write any integral which starts from this lower bound, let's say t1 to t1 plus t2. Sorry, this should be t2. Yeah, that's a mistake. Sorry. D tau, and then t1 to tau d tau prime of this u hat beta g tau u hat alpha g tau prime, just for the path, as this function, right? You can just write it. You can, so essentially you've achieved your goal, which is to get this double integral to start from 0. So you can write it as g beta alpha t2 essentially, as we'll see in the future, right? And then lastly, you have the third property, and it's definitely not the simplest one. It's going to be the hardest one. So let's tread carefully. And the third one is 0 to t1 d tau, 0 to t2 d tau prime u hat beta g tau, u hat alpha g tau prime. And we need to deal with integrals of this form. Now, the issue with this is that uh, it's here. It's quite obvious that this, we need it to be tau. So we want the integrals to be nested. In this case, the integrals are not nested. Tau runs from 0 to t1 and tau prime runs from 0 to t2. So they're not nested. And then if they're not nested, you can't write them as g beta alpha. So we want to decompose this in such a way that we write it in terms of your g beta alphas, right? So you can maybe put in the 1 upon h bar square here. Okay, maybe I should just do it for every place right now that, uh, yeah, so even this one should have a 1 upon h bar square, 1 upon h bar square, then 1 upon h bar square. You just put in a 1 upon h bar square everywhere. Okay, this one doesn't need it. Then you have 1 upon h bar square. Hence, this is equal to this. Yeah, okay. I'm just putting the 1 upon h bar squares to be more consistent with the definition of the g function. So, yep. So, if I can get this to look something like 0 to tau instead of t2, then I can write it as g beta alpha something something, right? And then that serves our purpose because at the end of the day, you want to use your cumulant approximation technique to write everything in terms of this g beta alpha. So that's the reason behind doing this. So what people call these integrals are of the form h beta alpha t1 t2, and then you want to write it in terms of some combination of g beta alphas, right? That's what we want to do right now. So let's visualize this a bit graphically, otherwise it will be a bit hard to do. So what I want to do is visualize the region of integration. So it's a double integral over two variables, tau and tau prime. So I put tau on the x-axis and tau prime on the y-axis. So tau prime is integrated from 0 to t2, as you can see, and tau is integrated from, I should move this up a little bit, sorry. Um, yeah, and tau is integrated from 0 to t1. So let's just say this is t1, right? I hope this is clear. So this is the region of time over which I want to integrate this function, right? So I can call this ROI, or region of integration. Uh, and now the subsequent proof is very mathematical, or very graphical, I would say. So if this is T1, right? So it would it's supposed to look like a square, and if this is T2, then you have this region, right? And you want to calculate this region of integration. So what I can do now is, I'm sorry, it doesn't look too good. I'll have to redraw this a little bit. Mm, okay, I'll move this out. This is tau prime, and then if this is T1, T1 should be somewhere around here. Yep, this makes more sense. It looks more like a square. So this was H beta alpha T1 T2. Right. So this. So what I could do right now, I'm going to change colors, is I want to calculate this region of integration. But to calculate this region of integration in terms of g functions means that firstly your integral must be nested. So what does that mean? For your integral to be nested, it should look something like 0 to some time d tau, 0 to tau d tau prime. So d tau prime, so tau prime must lie between 0 and tau. So that means that tau prime must be always lesser than tau. So this line which you draw along your diagonal of this graph, right, which is your region where I'm plotting my region of integration, this is equal to tau. This is tau equal to tau prime. So if I go to this part here, or this part here, so anywhere below the, I'll erase this out, anywhere below this line, in this part, tau prime is lesser than tau. That's quite obvious to see. You can just pick out some point, which is very logical. So you pick, let's say, this point out, and then you can quite obviously see that tau is this large, and tau prime is merely this. So if this is the line where tau is equal to tau prime, this region is the region where tau prime is lesser than tau. So it satisfies this criteria. So you want to essentially get these sort of integrals. So what I'm going to do is, if I want to get this region of integration, what I will do right now is I will calculate this integral, this complete integral, Then after that, what I will do is I will subtract off this integral, and lastly, I will add this integral. I hope that's clear. Because firstly, I will calculate this full thing, then I will subtract this off. So what I'm left with is this trapezium sort of thing. And then lastly, I will sum this up to this trapezium, this triangle. So I get this total rectangle, right? So it's like a very simple, like school geometry problem, right? So that's what I want to do. And you must be wondering, why do I want to do this? Because you will see the intuition very clearly soon. Let's say I want to calculate this integral, right? So this integral has this following form where you're integrating from tau is being integrated from 0 to t1, and tau prime lies within tau, right? So 0 to t1 d tau, 0 to tau d tau prime of this function. So it's 1 upon h bar square. You had beta g tau, you had alpha g tau prime, but on so many. So if I call this, I should refer to it by red, right? So this is your red contribution. And then secondly, what I'm going to do is I'm going to subtract off this purple contribution here, right? So what does this purple contribution mean? It means the integral from the lower bound t2 to the upper bound t1 along tau, right? D tau, and then tau prime lies within tau. So that would be this nested integral, right? Because I just previously, just very like 2 minutes back, I explained that this region corresponds to the region where tau prime lies within tau, right? And then the same integral. I hope this is clear. So by doing these two integrals, what I'm doing is I am calculating this area, right? So I've calculated this area out. Now, last thing which I would want to do is essentially sum this area into that calculation. So what I will do is add, and now in this case, I'm in a region which is across this line. So I'm in this side of the line. So in this case, tau lies within tau prime. So in this case, tau lies from 0 to tau prime. So in this case, tau will be the inner integral and tau prime will be the outer integral. And tau prime is being integrated from 0 to t2 as can be seen here. So I will write the 1 upon h bar square, that's from the function, of course, 0 to t2, d tau prime, 0 to tau prime, d tau, because in this region, repeating one last time, that tau prime is larger than tau, right? You write the function then. You had beta g tau, you had alpha g tau prime. Now, one very easy thing to do here is just to swap tau and tau prime. Because again, the way you think about this now is that they're just variables of integration, right? So you can go to 1 upon h bar square, 0 to t2, t tau, 0 to tau, t tau prime. And then you'll have u hat beta g tau prime, u hat alpha g tau. Okay, so but, and then this is equivalent to, I hope this is a little bit easy to see based on the proofs which we have uh, completed previously, but this is just equivalent to, so let me just tell you this. This is equivalent to u hat beta g tau minus tau prime, u hat alpha g 0, and then this is just equivalent to u hat beta g tau prime minus tau, u hat alpha g 0, right? I think it's quite clear to see what I'm going to do now. I'm just going to use the previous proof as C beta alpha minus T is C alpha beta T star. So this with the 1 upon h bar square, uh, this integral, the third integral, using this, I shouldn't erase this, I should still keep it. So using this property, this third integral just boils down to this 1 upon h bar square, 0 to t2, t tau prime, 0 to tau prime, d tau, 0 to tau, t tau prime of, okay, I shouldn't be writing the c 1 upon h bar square, but I can just write it as c alpha beta t star. And I hope that's clear. So now this can be just, this is equivalent to doing the integration first and then taking the complex conjugate. So I hope that's clear. So let's evaluate the second integral now. And I apologize, but there has been a typo here. So when I'm evaluating the second integral, which is this region of integration, right? So tau goes from t2 to t1, that's correct. But tau prime, the lower bound of tau prime would also be t2. I hope that's easy to grasp from here that this tau prime, its lower bound also starts from t2, right? And of course, it's lesser than tau. So this would be the correct expression. So I apologize for that. So now you take your second integral and we have to simplify it a little bit. So the simplification is quite simple actually in this case because it follows very well from our property which we just talked about, which is essentially this common state here t1 to t1 plus t2. In this case it's the opposite way around. You can just write it as the difference in times. Essentially what I'm trying to say is in this case it's t1 plus t2 minus t1, and that gives the upper bound to your integral here, right? And then you can simplify your integral very simply. So if that's confusing, please look at it very carefully. So the second integral can just be written as minus 1 upon h bar square, 0 to t1 minus t2, d tau, 0 to tau, d tau prime, and then you have u hat beta g tau, u hat alpha g tau prime. I hope this is clear. So let's go back to writing the h, the integral which we wanted to evaluate, which is, sorry, not h bar, I apologize. It's h uh, beta alpha, which depends on two variables t1 and t2, and can be written as the first integral, which is g beta alpha t1, and then the second integral right above minus g beta alpha t1 minus t2, and the third integral which is just plus g b alpha beta t2 star. So if you're confused about anything, I urge you to go back and look at this proof. So if we have any integral of the form which is not nested and integrates over specific times t1 and t2, we can write integrals of those form using the line shape functions. So these three properties which I've introduced are extremely important. And if there is any confusion in any of these three properties, I urge you to go back and look at the derivations really carefully and to think about them by yourself. So now we are finally at the position where we can evaluate F1. So let's start by evaluating F1. I'm going to not write the T1, T2, T3 notation. I hope it's clear that these dephasing functions are a function of T1, T2, and T3. So I will write it as the negative time-ordered exponential I upon h bar from T1 to T1 plus T2. You had e.g. tau, t tau, and a positive time-ordered exponential from 0 to T1 plus T2 plus T3. You had e.g. tau, t tau, and this is Bath ensemble average, right? So from the linear response theory class, I'm not going to go ahead and generate the cumulants in this case. So what we can do is from the linear response theory class, and what we took out was that some positive time ordered exponential or a product of a few, as we will see in the nonlinear response theory, can be written as the exponential of the essentially of the second order cumulants, right, which are integrated, of course, because that's the way it works. But it can be written as the exponential of contributions which are your second order cumulants. We don't need to go ahead and prove this, but it's quite obvious from our previous proofs, right? From linear response theory. So I'm not going to go ahead and do that. I'm just going to go ahead and pick all the second order terms in this case. So I will go ahead and expand this out. So what I will get is 1 plus I upon h bar. So now I'm going to use property number 1 of the integrals, where I can write this as 0 to t1 plus t2. You had e.g. tau t tau minus I upon h bar 0 to t1. You had e.g. tau t tau. I hope this is clear. And then the last thing which I'm going to do is take the second order term, which is plus I upon h bar square. This plus I upon h bar square just gives you minus 1 upon h bar square. So I'm going to do that. And then the integral is from t1 to t1 plus t2 d tau. And then the second integral will also run from t1 to tau t tau prime. And then you have u hat e.g. tau, u hat e.g. tau prime. I hope this is clear, because if tau runs from t1 to t1 plus t2, then the inner integral also lies between t1 and tau. I hope that's quite clear. If it's not clear, please think about it very carefully why there should be a t1 here and not 0. And you can go back to property number 2 of your integrals. And as I mentioned to you, you can just write this as 0 to t2. So I'll be doing this really quickly in the future for these second order terms, because we already proved it, and I hope that's clear. Now, for the next term, I expand this out to second order too. You don't need to expand further, because we only need terms till second order. Minus I upon h bar 0 to t1 plus t2 plus t3. You get u hat e.g. tau t tau. And then you get minus 1 upon h bar square, which is essentially plus minus I upon h bar square, which gives you this sort of term, right? And then you have an integral from 0 to t1 plus t2 plus t3, t tau, 0 to tau, t tau prime, and then you have the two integrals. I mean the two terms. You had e.g. tau, you had e.g. tau prime. I apologize for this sloppy writing. I should um clear this out. Write it here, and then this should come here, and then this will just come here. Okay. Dot 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 dot, and then yep. So you can close this out. Now I would just directly go ahead and pick out the second order terms and approximate it as the exponential of these second order terms, and that's the entire idea of the second order cumulant approximation, right? The expectation of the exponential of an operator written as the exponential of the expectation of that operator. So I'll pick out all the second order terms. So the first second order term which I will pick out is this multiplied by this. So let's do that out first. So you get I square, which is minus 1. So you get plus 1 upon h bar square. and then 0 to t1 plus t2, t tau, 0 to t1 plus t2 plus t3, t tau prime, and then you have u hat eg tau, u hat eg tau prime, which is the path ensemble average. And just note that when I multiply these two, right, I have to take different variables of integration over which I integrate over. They can't be identical, of course. They're just dummy variables, right? Next, I would just take this term and multiply it with this. Quite simple. I square would be minus 1. So you get plus minus, yes, minus 1 upon h bar square. 0 to t1. Please be careful with the order. Don't swap them around. 0 to t1 plus t2 plus t3, t tau prime. And then you have the same thing. U hat eg tau, u hat eg tau prime. And are there any other terms which we have to calculate or count? Yes. Which is just this term and this term individually. Right? So you get minus 1 upon h bar square, which is 0 to t2, t tau, 0 to tau, t tau. These are already very well set, so we don't really have to do anything with these terms. So you get u hat eg tau, u hat eg tau prime. And then you have your last term, which is minus 1 upon h bar square, 0 to t1 plus t2 plus t3, t tau, 0 to tau, t tau prime, u hat eg tau, u hat eg tau prime. So all other terms are just ignored under the second order cumulant approximation. So the third and fourth integral, very easy to handle, already set up for you. So what we need to handle very carefully are integral number 1 and 2. So for integral number 1 and 2, we have to use property 3 of the integrals, where you are integrating from 0 to some arbitrary time and from 0 to some other arbitrary time, and they're not nested, essentially. So just to recall, h beta alpha t1 t2 was written as g beta alpha t1 minus g beta alpha t1 minus t2 plus g alpha beta t2 star, right? So we write the first integral that way, exponential, which is just g t1 plus t2 minus g this first argument minus the second argument. So t1 plus t2 minus t1 minus t2 minus t3, which will give you GEE minus t3, correct? Plus GEE star, the t2 argument is t1 plus t2 plus t3. I agree that it's getting a bit confusing. So what I will do for now, I write this as tau 1, tau 2, so that it's a bit more easy for you to understand. Tau 1 minus tau 2, and then this is tau 2. And then this tau 1 and tau 2 correspond to this tau 1 d tau 0 to tau 2 d tau 2 of your C beta alpha tau 2. So I call this d tau prime. So tau prime. Right. So this is what h beta alpha is. So I hope it's clear that what I have to put in these terms here are just the upper limits in this case. In this case, it's just the first upper limit. In the second case, it's the subtraction of the first upper limit and second upper limit of the integrals. And in the third case, it's just the second upper limit, right? Now, the second term would give you a minus, and then you have GEET1 minus GEE. You have T1 minus T1 minus T2 minus T3. So you get minus T2 plus T3. Please do the math carefully if you're confused. And then you have plus GEE star T1 plus T2 plus T3. Right. Now you have a couple more terms which are just this green term is just GEET2. And this term is just GEET1 plus T2 plus T3. I hope it's clear till here. Quite obviously, one cancellation is very evident, which is this term cancelling out with this term. So in the end, you get 1, 2, 3, 4, 5, 6 terms, which is characteristic of this cumulant approximation. So you get exponential, let's arrange it well, minus GEET1 first, minus GEET2. Then you have your third term here, which is minus GEE T3 star, because GEE minus T3 is GEE T3 star using the proof, the property which we have proved already. Then you have plus GEE T1 plus T2, and then you have another plus GEE star T2 plus T3, and then you have minus GEE T1 plus T2 plus T3. So this corresponds to F1 approximately using the second cumulant approximation. So this concludes your derivation for F1. And likewise, you can derive F2, F3, F4, and let's proceed to do it. I hope there are no mistakes in my calculations. So let's quickly evaluate F2, and I won't talk too much about what I'm doing. I'm just going to go ahead and work the math out. So you go from 0 to T1 plus T2. You had EG tau, T tau, and then you have a positive time-ordered exponential, which goes from T1 to T1 plus T2 plus T3. You had EG tau, T tau. Again, we expand the terms out. So you get 1 plus I upon h bar from 0 to T1 plus T2. You had EG tau, T tau. And then you have a minus 1 upon h bar square for the second order term. 0 to T1 plus T2, T tau, 0 to tau, D tau prime. You had EG tau, you had EG tau prime. And then 1 minus I upon h bar. I'm going to split it again, 0 to T1 plus T2 plus T3. You had EG tau, T tau. Then you have another term, which is plus I upon h bar, 0 to T1. You had EG tau, T tau. And then you have minus 1 upon h bar square. Let me write it down a bit carefully and then explain to you what I'm doing. T1 plus T2 plus T3, T tau, T1 to tau, T tau prime, and then you had EG tau, you had EG tau prime. So the way we simplify this expression is just recast the lower limit to 0. This is T2 plus T3, so you remove the T1 from the bottom 2 and then make this 0 2. Right? That's just our property 2. And then in this case, the second order terms which I have to consider is this one with this one and this one with this one, and then I have these two terms sitting over here. So I approximated as the exponential of I square is minus 1, so 1 upon h bar square, 0 to T1 plus T2, T tau, 0 to T1 plus T2 plus T3, T tau prime. And you had EG tau, you had EG tau prime. And then you have another term which corresponds to minus 1 upon h bar square, 0 to T1 plus T2, T tau, 0 to T1, T tau prime. Then you had EG tau, you had EG tau prime, and then you have the remaining two terms. So I'm gonna skip a little bit here and note that you take the expectation with this term and then you take the expectation with this term. So it's essentially what you're trying to do is the expectation of this multiplied by 1, and then the expectation of 1 multiplied by this. That's what I'm trying to do here. So I'm just trying to collect all the second order terms from the product, right? So what that gives me is this first red term will just give me GEE T1 plus T2. I hope that's clear to see now. And then the second red term will give me GEE T2 plus T3. If this is not clear, please work the math out by yourself and confirm that it's the case. And then from the first term, I'm just going to use the same property as last time, GEE, the first upper limit, minus GEE, the difference in limits, which is minus T3, and then plus GEE star, the second limit, T1 plus T2 plus T3, minus GEE T1 plus T2 minus GEE T2 plus GEE star T1, right? And then we get minus GEE T1 plus T2 minus GEE T2 plus T3. So this cancels this out, and then you get six terms again. Exponential minus GEE star T1 plus GEE T2 minus GEE star T3 minus GEE T1 plus T2 minus GEE T2 plus T3, and then plus GEE star T1 plus T2 plus T3, and then this corresponds to F2. Now we continue and we work on F3, which is the negative time ordered exponential 0 to T1. U hat e.g. tau d tau, and then a positive time ordered exponential T1 plus T2 to T1 plus T2 plus T3. U hat e.g. tau d tau, path ensemble average, and I expand the terms again the same way. So you get 1 plus I upon h bar 0 to T1, U hat e.g. tau d tau, and then you get the minus 1 upon h bar square 0 to T1. Oops, I suppose I have made one mistake. It's actually quite a big mistake, and we have to clarify it right now before we proceed. And I apologize for this mistake. So you need to notice something very clear here, that these are negative time ordered exponentials and not positive time ordered exponentials. And I have made a mistake here with this term. If you recall, if it's a negative time ordered exponential, the arguments are changed. So it should actually be tau prime, then tau. Like if you recall from our previous classes, the earlier time argument comes first and then the later time argument for negative time ordered exponentials. And I apologize for that mistake. That's quite a big mistake because then you'll have a difference in complex conjugates. And I shall clear this out now itself. I apologize again. So in this case, what you get for these sort of terms is that you will get a complex conjugate instead of the actual term itself. So this was supposed to be GEET2, but this will be GEET2 star. And that's quite easy to think about because GEE minus T would be equal to GEET star. Right, so that was the mistake, and I'm sorry for it. GEE star, there should be a star here. Yep, and then this star was missed out here, and then this star was correspondingly missed out in the second part too, where you have tau prime here and then tau here. So, yep, apologize for it again. Right, so we made a mistake here. So this T1 plus T2 term should have a complex conjugate, complex conjugate, which we missed out. So I'm sorry for that. And now we need to do the same thing very carefully for the F3 terms. You have d tau, 0 to tau, d tau prime. Then you have u hat eg tau prime, u hat eg tau. So the order will get reversed, and then you get a complex conjugate based on the properties we have discussed. And then you get 1 minus I upon h bar, 0 to t1 plus t2 plus t3, u hat eg tau d tau, plus I upon h bar, 0 to t1 plus t2, u hat eg tau d tau, and then you get a minus 1 upon h bar square from t1 plus t2 to t1 plus t2 plus t3, t tau, and then from t1 plus t2 to tau, t tau prime, u hat eg tau, u hat eg tau prime. Right, and then using the property we discussed, and then this can just be written as this. And this can be approximated as exponential. This time I'm just going to straight up go ahead and write the terms like how I did the previous time, but for the first two terms I'll have to carefully do it. So again, no rushing it. So we have this term multiplied by this term. So you get I square minus 1, 1 upon h bar square, 0 to t1, d tau, 0 to t1 plus t2 plus t3, t tau prime of u hat eg tau, u hat eg tau prime, trace the path. Then you have this term multiplied by this one. So you get minus 1 upon h bar square, 0 to t1, t tau, 0 to t1 plus t2, t tau prime, u hat eg tau, u hat eg tau prime, path ensemble average. And then you have these two terms, which is minus, this I'm first considering this term and then this term, right? So which will be minus GEE T1 star, the star because of the negative time ordered exponential second term. Then you have minus GEE T3. And this will give you F3, which is equal to exponential GEE T1 minus GEE star T2 plus T3. I urge you to think of it carefully and do it slowly if you're confused here. Plus GEE star T1 plus T2 plus T3 minus GEE T1 minus GEE star T2 plus GEE star T1 plus T2 minus GEE star T1 minus GEE T3. So this cancels this, and then F3 is equal to exponential minus GEE star T1 plus GEE star T2 minus GEE T3 minus GEE star T1 plus T2 minus GEE star T2 plus T3 plus GEE star T1 plus T2 plus T3. So this holds good. And lastly, we derive F4, which is the positive time ordered exponential minus I upon h bar from T1 plus T2 to T1 plus T2 plus T3 UEG tau d tau. And in this one, I'm going to skip a lot of steps because the procedure is identical, and I urge you to work it out on your own. Right. So this will be equal to, approximately equal to the exponential of, okay, I have to expand it first. 1 minus I upon h bar 0 to t1 plus t2 plus t3 u e g tau d tau, and then you'll have a plus I upon h bar 0 to t1 plus t2 u e g tau t tau. Then you have a minus 1 upon h bar square from 0 to t3 t tau 0 to tau t tau prime. You had e g tau, you had e g tau prime. Then you have this, the second term, 1 minus I upon h bar 0 to t1 u hat e g tau t tau plus minus 1 upon h bar square 0 to t1 t tau 0 to tau t tau prime u hat e g tau tau prime. In this case, we don't have to worry about the ordering of anything because they're both positive time ordered exponentials. Then the first term which we can account for is this multiplied by this. Second term would be this multiplied by this. And then your third term would be this, and your fourth term would be this. Right. So it's approximately equal to the exponential of your first term will give you a plus. I'm just going to go ahead and write the terms this time. GEE T1 plus T2 plus T3 minus GEE T2 plus T3 plus GEE star T1, which I'm just doing merely by observation, but I do not urge you guys to do that. And this should have a minus sign on the outside, right? And then the next one will have a plus sign. GEE T1 plus T2 minus GEE T2 plus GEE star T1, right? And then you get minus GEE T3 minus GEE T1, right? And then you get this cancels this. So you get exponential minus GEE T1 minus GEE T2 minus GEE T3 plus GEE T1 plus T2 plus GEE T2 plus T3 and minus GEE T1 plus T2 plus T3, and this is F4. So we have successfully derived all four dephasing functions. So now in summary, we will summarize all your response functions R1 through R4. So R1, which is your non-rephasing stimulated emission for your two-level system, is equal to mu Eg to the power 4, which is your oscillator strength square, exponential minus I omega Eg, T1 plus T3 times F1, which we have an exact expression for, which is exponential minus GEE T1 minus GEE star T2 minus GEE star T3 plus GEE T1 plus T2 plus GEE star T2 plus T3 minus GEE T1 plus T2 plus T3. So this is the complete expression for R1. R2, which is your rephasing stimulated emission expression, is equal to mu Eg to the power 4 exponential minus I omega Eg T3 minus T1 times exponential minus GEE star T1 plus GEE T2 minus GEE star T3 minus GEE star T1 plus T2 minus GEE T2 plus T3 plus GEE star T1 plus T2 plus T3. I hope this is clear. Then we go to R3, which is your rephasing ground state bleach, and is equal to the oscillator strength squared exponential minus I omega Eg T3 minus T1 times exponential minus GEE star T1 plus GEE star T2 minus GEE T3 minus GEE star T1 plus T2 minus GEE star T2 plus T3 plus GEE star T1 plus T2 plus T3. And lastly, we have R4, which is your non-rephasing ground state bleach, and that is equal to mu Eg to the power 4 exponential minus I omega Eg T1 plus T3 times exponential minus GEET1 minus GEET2 minus GEET3 plus GEET1 plus T2 plus GEET2 plus T3 minus GEET1 plus T2 plus T3. So we have completely derived R1 through R4, where the dephasing functions F1 through F4 are calculated under the second order cumulant expansion technique. And these GEE line shape functions, or the autocorrelation line shape functions, correlating uh, the fluctuation in transition energies of the two level systems separated by time t and integrated twice to give you the autocorrelation line shape function for the specific transition, is defined as 0 to t, like I just described it out, but let me write it down again. T tau prime of the autocorrelation function CEE tau prime. Right. And then the CE tau prime is just 1 upon h bar square, and the correlation function of the energy gap operators separated by time tau prime. So this brings us to the end of our derivations for our third order nonlinear optical response functions for a very simple minimalistic two level system. So from these R1 to R4 expressions which are derived, you can now input a form of your correlation function CEE tau, correspondingly calculate your autocorrelation line shape function, and subsequently you can model any third order nonlinear optical response experiment. But these are more or less restricted to 2D ES. So in the case of 2D ES or pump probe 2, you can use these expressions for pump probe 2. But in the case of 2D ES, you can model a diagonal peak corresponding to the excitation at state E with average transition frequency omega EG and detection at omega EG2. So I would urge you to start simulating or to perform simulations with these R1 through R4 with any simple phenomenological model for your correlation functions. And this brings us more or less to the end of this series where we calculated the third order nonlinear optical response functions for a simple two level system. And I hope you gained a lot from this. I know that there was a lot of math and nitty gritties which we had to go over. And thank you for bearing with me. And we will discuss some other aspects later on, hopefully. So we'll meet then. Thank you. Bye bye.